So, hello everyone. I'm Diamond Baker, and my article for this presentation is on the oxidation of aldehydes to nitriles with oxoammonium salt, and that's preparation of Piperonylonitrile. hmm So, the scale and optimization. Let me go ahead. Scale of optimization of this experiment. The initial amount of the products that were used was the largest scale ran for the entire reaction. The experiment was redone on half a scale, and the following reagents that were used were purchased through a commercial source and with used without like further purification. There was not price. It was no price that was mentioned in the journal article. However, the experiment used relatedly expensive, relatedly inexpensive materials. The most expensive reagent used in the experiment was HMDS, and that usually goes for $213.75 from the source Spectrum Chemicals. So the checking process that the authors use for this experiment, the checkers, this experiment was checked by Charis A. Roberts and Richmond Sarsbaum. The checkers did not make any additional contributions or comments to the initial run of the experiment. However, they ran a second experiment on half the scale, like I said in the beginning, and then this was reported afforded isolated yields of 87 and 73%. So the reaction setup or apparatus, they use a single necked 500 milliliters round bottom flask that was connected to a 24/40 joint. The flask was equipped with a Teflon coated oval magnetic stir bar that's around like two centimeters times 2 centimeters times 4 centimeters, and left in the open. The flask was placed into a room temperature water bath, which ranged around like 26 Celsius degrees. So the reagents that I did use, these are in the starting materials. So I started off with piperonal, and that started off with the mass of 10.51 grams, and then with the millimoles of 77, and then the equivalents of 1. I did also had use 140 milliliters of dichloromethane, and then also used pyridine that was used. It was around 6.1 grams and 77 millimoles and 1.1 equivalents. Also, hexamethyl disilazane, which is commonly called HMDS, was used also with the grams of 28.2 grams, 175 millimoles, 36.7 milliliters of volume, and then a 2.5 equivalent. Then oxoammonium salt was used. That was 52.5 grams, 175 millimoles, 2.5 equivalents. And then last but not least, diethyl ether, and that was 200 milliliters. So, any special precaution of the reagents, except for the conventional precautions, there were no particular precautions for the chemical reagents due to the irritating properties of each reagent. Standard suitable PPE, such as gloves, goggles, and a lab coat, are essentials during the experiment. And then the limiting and the access reagent. So in the experiment, the limiting reagent, the piperonal, due to its equivalence of 1. The access reagent is hexamethyl disilazane, the HMDS, I'm just going to call that, and then the oxoammonium salt. were both 2.5 equivalents. So that was the access reagent. Why is access necessary? This is required to guarantee that the reactant react completely with the limiting reagent, which is the piperonal. So for the procedures, a single necked 500 milliliter round bottom flask with a Teflon coated stir bar was equipped and then left open to the air. And then uh, uh, 10 point, 10.51 grams of piperonal and 140 milliliters of dichloromethane was added to the flask. And then the flask was placed into a water bath with, and then that's when the magnetic stirring started or commenced. And then allow the contents in the flask to stir for 2 minutes for completion of complete dilution, which is meaning the breakdown of the solution. And then the 6.2 milliliters of the pyridine was added, followed by the addition of 36.7 milliliters of the HMDS. And then allow the solution to stir at room temperature, 26 Celsius degrees or degrees Celsius for 5 minutes. And then afterwards, the oxoammonium was added 52.5 grams to the flask via a plastic powder funnel gradually over a 2 minute period. And then the powder funnel was removed, and then the reaction temperature was monitored afterwards. Then afterwards, there was observe the color change of the solution in the flask and access the reaction progress by crude HNMR and GS/MS. And then with the color change, for me, it was it started off yellow, then progressed to orange, and then it went to a red, which was the next step was that the solvent and the vacuum by rotary evaporation was to give a thick red residue substance. And then afterwards, the residue was titrated with the addition of 200 milliliters of diethyl ether. Afterwards, the sides of the flask was scraped with a spatula to release all solid material. Then the magnetic stir, and then the flask was magnetically stirred again to allow pulverization, which is the grinding of the solutions or the solvent. And then afterwards, all magnetic stirring ceased or stopped. And then a vacuum filtration was prepared using a 150-liter coarse porosity centered glass Buchner funnel, which had a 7.3 centimeter diameter, and that you would fit the funnel to a 1 liter filter flask. Afterwards, the suspension was poured through the filtration setup using 50 milliliters of diethyl ether. Afterwards, the precipitate was collected and then washed with another 100 milliliter of diethyl ether, and then transfer the remaining filtrate to a 1 liter separatory funnel, then wash sequentially with 2 moles of hydrochloric acid HCl. This was done 3 times, and it was 150 2 moles. That's like equivalent to 150 milliliters, and then also with saturated sodium bicarbonate and a HCO3. That was also done twice, again on 150 milliliters, and then 200 milliliters of brine. Afterwards, uh, the solvent was dried. The dry layer with the solvent was dried with a sodium sulfate and a SO4 and removed by gravity filtration. Afterwards, that's when the solvent was removed and vacuumed by rotary evaporation to receive the percent yield of the crude Piperonylonitrile. And then that's when purification happened. Purified the nitrile by recrystallization using a minimal of, which is 40 milliliters of hot, which is equivalent to 60 degrees Celsius, of a ratio of 7 to 3, mixture of hexanes and ethyl acetate. And then afterwards, the solution was set out to cool to room temperature for 15 minutes and then placed into a freezer at -4 degrees Celsius for 2 hours. And then afterwards, the solids was collected by vacuum filtration through a 60 milliliter fine porosity Centire glass Buchner funnel with a 5.1 centimeter diameter. And then afterwards, finally, the collection of the crystalline was collected, and also the percent yield was calculated. Right here is the workup of the reaction, or the rotary evaporation up here. Pretty much that's when the flask was just put into some water and then it was just spun in the water. And then here also, this is where the titration happened, and not the titration, sorry, the extraction of the filtrate. This is when the dry layer, the layer was dried with the sodium, the sodium sulfate, and then it was separated. So for the reaction workup, to quench the reaction, the solution was left to stir at room temperature for 5 minutes. With that procedure, at which point the oxoammonium salt was added. 52.5 grams was added to the flask viva plastic powder funnel gradually over 2 minutes, and then the reaction was stirred at 26 degrees Celsius, and color change is noted, starting yellow and progressing through orange until finally reaching a deep red color. Then the solvent is removed and vacuumed by rotary evaporation to give a thick residue. That was up here. So, and then down here, this is when the reaction was titrated. And then the residue was titrated by the addition of the diethyl ether, which was the 200 milliliters, resulting in a suspension of the spent oxidant. The sides of the flask were scraped with a spatula to release all solid material. And then the flask, which can still contain the stir bar, was magnetically stirred to allow for pulverization, which is the grinding of the solids, thus maximizing leaching of the piperonylonitrile into the mother liquid. So as you can see here, this is where the liquid was, it looks like it's separated a little bit, while the solvent, the thick powdery solvent, was at the bottom. Then to add on to the workup, the vacuum filtration of the reaction, that's when the 150 milliliter Buchner funnel was fitted to a 1 liter filter flask, and then the suspension was poured through the filtration setup to remove the orange precipitate using diethyl ether, 5 milliliters of diethyl ether, to ensure complete transfer from the flask. And then the precipitate was collected. The collected precipitate was then washed with, again, diethyl ether, 100 milliliters, to yield the recovered spent oxidant. Then here is the extraction. This is where the orange filtrate is then transferred to a 1 liter separatory funnel and then washed subsequently with 2 moles of hydrochloric acid, and then saturated with NaHCO3, and then also brine. And then the organic layer was then dried over with the sodium sulfate, which is removed by gravity filtration. And then the solvent is removed and vacuumed by rotary evaporation to yield a 9.91 grams, which is 96% of the crude piperonylonitrile. So for purification, this is when the solids was collected by vacuum filtration to yield the crystalline, and as this is here, right here. And then to purify, recrystallization was used. The nitrile was used to do the recrystallization, a minimal amount, which was the 40 milliliters of the 7:3 ratio mixture of the hexane and the ethyl acetate, which fully diluted. The solution is cooled to room temperature for 15 minutes and then placed into a -4 degrees Celsius freezer for 2 hours. This method was used to avoid the use of chromatography. However, chromatography will often give a slightly higher yield of the desired product, but the authors just decided just to do recrystallization for this experiment. And then purification can also be accomplished by the passage of the material obtained after the workout, the crude material over a short pad of the silicon pad or just silicon, eluting with a 9-to-1 ratio mixture of hexane/ether. And then here is the sample of the piperonylonitrile isolated after the workup, and then the piperonylonitrile isolate after recrystallization. So for characterization and proof of purity, or a little typo, it's supposed to be of, but TLC was also done. I wouldn't say the TLC was asked for the proof of the purity, but it could have been more of the characterization of the final product. So the conditions were followed as like 20% of ether and hexanes, visualized with a 2254 nm UV lamp, and then nanometers. Then the starting material and the products had very similar RF values, which the piperonyl equals 0.33, while the piperonyl nitrile equal to 0.31. Monitoring the reaction by TLC can be challenging due to similar RF values. Here is the TLC where the product and the starting material, the RS values were observed here. You can just see like the lines were very close to being at the same point from the solvent front. And then as for pure proof of purity, NMR was used, and with that, yeah, yeah. So, and then NMR, sorry. So with an NMR, the quantitative NMR analysis showed this product was 97% purity or purified. And then the monitoring the reaction with the NMR is more useful in this case. The characteristics of the aldehyde peak can be observed at 9.81 ppm, and the characteristics of the aryl CH bond for the product can be observed at 7.04 ppm, and HNMR spectra of the crude reaction mixture. So the safety note of this experiment and the hazard warnings, it really wasn't as dangerous or any bad chemicals that were used, or they're all strong, and they did have very like throat or nose irritant. So the main critical thing was to have on appropriate PPE in the lab, which is the lab coat, the goggles, the gloves, closed-toed shoes, etc. It's required when potential, of course, exposure to hazardous materials such as hazardous chemicals or biohazards. Proper PPE and laboratory attire helped minimize the potential for skin exposure to hazardous chemicals and so on. And then for as like the dangerousness of this experiment, it's quite safe. So as long as the safety lab measures are followed, it should be good. And then to add on to that, all chemical waste should be disposed in accordance with local regulations. So it should be disposed correctly, not straight into the drain or the garbage. And then the entire experiment should be conducted in a well-ventilated fume hood. proper procedures and precautions in handling waste and chemicals. Are flammables, liquids slash solids, are toxic if swallowed, and can cause eye and skin irritation or damage, or are harmful if inhaled. Most of the reagents used in this experiment were not considered hazardous by commercial sources. Prior to performing each reaction, a thorough hazard analysis and risk assessment should be carried out with regarding to each chemical substance and experimental operation on the scale plant and in the content of the laboratory where the procedures will be carried out. So here is the mechanism of the experiment. Here is showing the mechanism of oxidation of alcohols using the piperonal under weak, basic, and neutral conditions. So this oxidant is thought to operate via a hydride transfer mechanism from the alpha CH bond of the carbonyl of the electrophilic oxygen of the oxoammonium salt, which is shown here in this picture, under a non-basic under a non-base assisted condition, the transition state is similar to the putative oxocarbenium ion, and thus the rate of oxidation reflects cation stability. And this disparity in rates allowed for selective oxidation. Secondary alcohols can be selectively oxidized in the presence of a primary alcohol under neutral or acidic conditions. Under weak basic conditions, the hydride transfer and the depronation events are likely concerted. The key difference is the formation of the pre-oxidation complex, that is a direct result of intermolecular hydrogen bonding between the base, typically pyridine derived, and the alcohol. As such, this process is now under steric control, and primary alcohols can be oxidized selectively in the presence of secondary alcohols. And so, further elaboration of the action of this oxidant has revealed that it can engage in an array of oxidative functionality processes. These include methods to perform oxidative esterification, oxidative amidation, oxidative nitrile formation, oxidation of cyclohexadiones to oxidation of alpha pure fluoroalcohols, and dehydrogenation of pure fluoroalkyl ketones. So right here is shown the recently developed oxidation functionality using the HMDS. And then here are the application of the HMDS as an oxidant for alcohol oxidation and beyond. So the mechanism of this reaction is the formation of the N-trimethylsilylamine, which can undergo facile oxidation via a through space hydride transfer to the oxoammonium salt. And in addition, the byproducts of this reaction is boron trifluoride, which accelerates the initial condensation of HMDS with a aldehyde. Note that the conditions are not regularly dried, and the mechanism is dependent on the sole hydrolysis of HMDS to the monocylated amine. The procedure described here can be applied to the conversion of many aldehydes to nitriles, although the means of purification will vary depending on the structure. And then, taking advantage of the well-established ability of the oxoammonium salt to convert alcohols to aldehydes, a two-step one approach to the conversion alcohols to nitriles was also realized. The first step of this process utilized lutadine to avoid undesired acyl pyridium formation and hence oxidative dimerization of the resulting aldehyde. The second step utilizes the condition described here and can be initiated without the isolation of the aldehyde. And then, in summary, the oxoammonium salt is a robust reagent for not only routine oxidization but for oxidative functionalization. Detailed in this procedure is a means to convert aldehydes and alcohols to nitriles under very mild conditions with a broad scope. As a result, this process offers a user friendly means for the late stage installation of a nitrile group in advanced systems. Ooh, my bad. And then the computational analysis of the mechanism confirmed that aldimine formation was very favorable and realized that the reaction proceeds through a hydride transfer mechanism. A robust catalytic variant of this process with a wide substrate scope has been described, even though the importance of the nitrile to the medicinal and the agrochemical communities, as well as some to the operational challenges of oxidizing amines, substrates, other avenues of the oxidative generation of nitriles were explored. So these were the authors of the article. Professor Christopher B. Kelly, he obtained his bachelor's in science degree in biochemistry from Stonehill College in Easton, Massachusetts in 2010. And then that same year, he began his PhD studies at the University of Connecticut, UConn, under the guidance of Dr. Nicholas Leadbeater. He created innovative synthetic techniques in organofluorine and oxoammonium salt chemistry while at UConn. And then he joined another Professor Gary Molander's lab at the University of Pennsylvania, UPenn, or Penn, as a National Institutes of Health postdoctoral scholar after receiving his PhD in organic chemistry in 2015. And then he pioneered synthetic approaches in the field of photoredox catalysts. While at Penn, he began his career as an academic in Virginia Commonwealth in 2018 before transitioning to business as a member of the Janssen's newly created Discovery Process Research Team. And then here we also have Kyle Lambert. He graduated from the University of New Haven in 2012 with a bachelor's degree in both science and forensic science. 2017, he received his PhD from the University of Connecticut, where he worked under Professor William Bailey. He dissertated study focused on oxoammonium salts, which was used in the experiment as a selective oxidant and conformational investigations of saturated heterocycles. And then he also joined another professor, John Wood, at a lab at Baylor University as a National Institute of Health postdoctoral research after finishing his doctorate, where he explored natural products synthesis. And then he became a assistant professor at Old Dominion University in 2020. The interests of his new research groups are the development of innovative synthetic methodology and the complete synthesis of psychological relevant natural compounds.